Alfred Holly-Hampton was indeed a brilliant scientist. In 1925, his discovery played a fundamental part in the development of quantum mechanics and offered further evidence to support the wave-particle duality of light. The phenomenon we're going to discuss in this video is the inelastic scattering of a highly energetic X-ray photon from a free electron in a carbon target. It was named, to no surprise, after its discoverer as the Compton Scattering effect. As you can see in the animation in the upper right corner, after the collision of an X-ray photon with a free electron at rest, the electron recoils and starts moving while the new X-ray, less energetic than the incident one, is scattered at an angle theta with respect to the initial incident direction. In order for the fundamental law of conservation of energy to hold, the new X-ray has to be less energetic than the original one, as part of its energy was transformed to the electron's kinetic energy, and hence a shifted wavelength is expected to be observed as the X-ray energy is inversely proportional to its wavelength. Now, before getting to the derivation of an actual equation to describe the wavelength shift, it is worth noting that any mention to a free electron in this video is an approximation. The free electron is actually an electron within the outer cells of the atom, where its atomic binding energy is so small compared to the large X-ray energy that it can be approximated as free.
The Compton scattering must be treated relativistically. As the electron is initially at rest, its momentum is zero. We'll call its momentum after the collision ρe, and the momentum of the photon before and after ρ0 and ρ1 respectively. From conservation of momentum, we know that ρ0 should be equal to ρe plus ρ1. Using vector addition and the cosine rule, we can derive an expression that relates the three momenta. Now, considering relativistic energies, we must make use of Einstein's relation. Since the photon is massless, that is travelling at the speed of light, its energies E0 and E1, before and after the collision respectively, are given by the momentum times the speed of light. The electron energy before the collision, EE, is simply its rest energy, me times c squared, while E prime after is given by the entirety of Einstein's relation. Notice the square root on the right hand side? Let's get rid of that by squaring both sides. Now, we substitute the relation we obtained before for ρe squared, and oh boy, that is a mess. Now let's try tidying this up by getting rid of the common terms in both sides. Okay, that looks nicer. Now, we know the momentum of a photon is its energy divided by the speed of light, and we also know the energy of a photon is Planck's constant multiplied by its frequency, and that the speed of light is given by the product of the photon's wavelength and its frequency. So, substituting all that into the equation, getting rid of the cancelling terms and rearranging for the wavelength shift, that is, lambda 1 minus lambda 0, we get an expression for the wavelength shift in Compton scattering. Notice that this shift is dependent on the angle theta and that it gets larger as the scattering wavelength increases. This means that as the angle increases, the new photon is less energetic and subsequently the electron gains more kinetic energy. You should notice the term h over me by c is a constant term consisting of entirely fundamental constants and is called Compton's wavelength.
The X-ray photon, as it reaches the carbon target, can either hit a free electron, an electron on the outer shells of the atom, or an electron bound within the inner shells of the atom. The latter is obviously more tightly bound by the positively charged nucleus. Therefore, as the X-ray photon is incident on it, it will cause the entire atom to recoil, and hence the colliding mass, in this case, will be the mass of the whole carbon atom. As the angle theta gets larger, the shifted wavelength further increases, and the two wavelength peaks get further apart.
Perhaps you may be wondering, why can't the electron simply absorb the photon? Well, that's the scenario we'll now discuss. Here's a little diagram in order to help you imagine. We can start by writing out the conservation laws, since we know these will hold no matter how this interaction goes. Since we've taken the momentum of the electron to be initially equal to 0, that makes the total momentum in the system before the interaction just the momentum of the photon. After the interaction, the only momentum in the system is the momentum of the electron. Though the photon may not have mass, it does have momentum, and since it has momentum, it also has energy. Its energy, E0, is equal to its momentum times by the speed of light. In the case of our electron, this makes its energy before the collision, EE, equal to the mass of the electron, ME, times by the speed of light squared. Lastly, we have the energy of the electron after the interaction, E1, which requires the full relativistic equation to define. This is because it has both mass and momentum. Now, all that's left to do is to plug equations 5, 6, and 7 into equation 4. Boy, it sure does look like a mess, doesn't it? Perhaps squaring both sides might solve this. Since the first of those terms is on both sides of the equal sign, we can easily cancel that out. Also, we know from equation 3 that the momentum of the photon is equal to the momentum of the electron. Now we have another term that's on both sides of the equal sign, so we cancel that as well. Now this statement doesn't make any sense, because that would mean that the momentum of the photon was 0. We know that c cubed is not equal to 0 since we know the speed of light. Therefore, we know that this interaction cannot take place.